especially the cheaper ones, still only use basically average angular velocity. So they don't pick up changes in angular velocity in one revolution. And that's something that Favero, and especially the Aciomas, have always done really well, is they have an instantaneous angular velocity reading.
So the company has developed a technology called instant angular velocity, which uses a 3-axis gyroscope to detect the angular velocity of the pedal stroke. Simply put, your power isn't continuous through a pedal stroke. There's more force between 3 and 6 o'clock and less at top and bottom of the stroke. Now, the company reckons most power meters use an average of its angular force, but its technology takes a real and instantaneous force, which contributes to a claimed accuracy of 1%.
You see, most recreational and amateur road cyclists don't have a consistent and smooth pedal stroke. It will vary based off flexibility, bike fit, poor technique, road conditions, the list goes on. However, many stock power meters will use something they call average angular velocity, where they're assuming the pedal stroke is efficient and the same. This assumption, from a study which granted is on the Accioma website, concludes that average angular velocity can lead up to a 4.5% error rate.
With 2.0.6 has introduced IAV power. This is instantaneous angular velocity. Favero have published a 27-page document on what IAV is all about. Look, in a nutshell, with the latest firmware, your Favero Aciomas will be accurate in the saddle, and the saddle, with round rings and with asymmetric rings or non-round rings. This average Aciomas is one of the power P1.
So what is instantaneous angular velocity, and does it actually make a difference when it comes to measuring power? Well, that's what we're going to get into in today's video, and the short answer is, yeah, it makes a difference, but not as much as everyone's saying. And under most circumstances, when you're riding outside, you can probably ignore the differences that Favero is going to make versus a Quark or a Power to Max.
Yeah. So when you're pedaling, you might be pedaling at 90 RPM, but if you take 1 RPM, one of those cycles, one of those revolutions, the speed of your foot is not constant throughout that revolution. And this is especially bad if you're outdoors and climbing or sprinting up steep gradients or at lower cadences.
Yeah, so that's generally true, except I would imagine that these oscillations would be worst indoors when you've got a really low flywheel mass in comparison to like an 80 kilo cyclist outside. So yeah, Pete Talk's absolutely correct in saying that outside, when you see these oscillations, it's going to be when you're pedaling up steep hills, because you're dealing with such high system forces, and the dead spot is going to give a lot of time for gravity to sort of slow you down. But when you're indoors, you've got a really low inertia compared to outdoors. And so these oscillations in torque, and that's something that Pete Talk didn't exactly touch on, which is these oscillations in angular velocity are coming from oscillations in torque, and they're actually like they lag these oscillations in torque as well. So there's a relationship between the two things, your sort of peaky application of torque and then a peaky profile of angular velocity.
And if you've ever been on a watt bike or any kind of bike fitting jig, you'll notice that
yeah, so this is massively exaggerated for what it would look like outside, because a watt bike again has like a low flywheel mass.
Cadence graph, or even your power graph, is essentially a peanut shape. And that's because it's not constant throughout the circle. So your angular velocity, your RPM, actually changes throughout the circle. If your power meter can't pick that up, it takes an average, and a lot of power meters will overread because they don't take into account.
So I don't think that these power meters will overread by averaging. Whether or not they overread, they underread, or produce any error at all really depends on the relationship between the torque that you apply and the angular velocity that you apply. If you apply constant torque and your angular velocity oscillates in some fashion, then these two quantities aren't correlated with each other, and you're not actually going to get an error when you perform averaging on torque, right? And averaging on angular velocity and multiply them together. But if the two quantities do vary across time and there's a correlation that develops between the two, then you're going to get positive error. You could get negative error as well. You could also have a case where they both vary in some fashion, but they aren't correlated with each other. And then you've got two sort of random variables, and you multiply the averages together and you get the average of the products as well. So there's a lot of things that could be happening there. I don't think it would necessarily produce overreading.
Like dips or troughs, peaks and troughs in the angular velocity measurement. Now, I wanted Favero to give me some more data about this, some more proof. So they sent me some experimental data, which is really cool, which basically shows predicted kind of...
Yeah, so, and this is why Pete Talk thinks that that the averaging effect will produce overreading, and it's basically because of this data. Now, I assume he hasn't looked at the paper, but in the paper, they perform an experiment with round and non-round chainrings. And this clump of data with high variation and high angular velocity is the non-round chainrings. So it's not so much the oscillation, the angular velocity variation, which is a bit of an interesting measurement anyway. I would have thought to use standard deviation or something more statistically valid. But it's not so much the variation that's producing error here. It's the fact, the categorical fact of using non-circular chainrings. So you can sort of see for the circular chainrings clump around here, and I'm assuming that this is basically the clump of circular chainrings, that there isn't really a correlation between angular velocity variation and power error. If anything, it might actually be negative.
Meter error based upon the variation of angular velocity. So if you've got if I'm doing this, like up a really steep climb, I've got a very peaky angular velocity through the pedal stroke, and then the more variable that angular velocity is, the higher the calculated power error is going to be. And we'll talk about this indoors when we look at power results from this.
So it's important to note that he's talking there about sort of peaky torque, and that peaky torque induces peaky angular velocity. But the relationship between those two things is not as simple as it might seem, because when you apply torque in a really peaky fashion for a given RPM, you actually introduce spectral components, frequency components that are above the fundamental frequency of the pedal stroke. And those like peaky spectral components are attenuated by the dampening effect of mass, right? This is something I'm going to get into, the sort of mechanical model of a cyclist. But it's, and I think that peak torque actually finds this conclusion later, which is that the peaky application of torque, like when you're standing, doesn't actually produce more error. It's sometimes if you have a smoother application of torque that's more sinusoidal, that's actually when you get more error. So just an interesting note.
Versus the cork on very short, steep, kind of peaky, standing, lowish cadence efforts. And I think it highlights quite a lot of error, whereas this is a gyro reading many times a second. It's going to take a bit more research to figure out if that cork is the same as a modern cork, because you can't put two spider power meters on the same bike. Let me actually ride the bike and enjoy it now, because I have to go really slowly when I'm talking to the camera, because the wind noise or the camera just bounces around too much.
All right, let's let him enjoy his ride. Manufacturers out there, Favero included, InfoCrank is also another company that make these sort of categorical claims about the superiority of their designs. So Favero claim to measure instantaneous angular velocity, and they claim that makes a substantial difference in terms of the accurate measurement of power. They published a paper, which we're going to get into, that Peak Torque alluded to, and we're going to do a bit more of a detailed technical analysis of that paper. And then InfoCrank, who are an Australian-based company, claim to sample torque at 250 hertz, 250 samples a second, which is quite a high rate of sampling torque, or at least they claim it's high relative to other manufacturers. And there are plenty of mechanical engineers who've weighed in the past on the topic of power meters. So Keith Wakeham owns a patent or two on power meters on behalf of Four Eyes, and then Peak Torque as well, famous cycling engineer YouTuber. He's weighed in on the topic. The thing is, they're mechanical engineers. So they're sort of looking at the strain gauge placement, and their big bugbear are these Shimano power meters, which are an asymmetrical design, which means that they're picking up parasitic strain, is what they call it, or strain, effectively strain outputs or torque outputs that aren't in the primary sort of axis that we're interested in terms of measuring and estimating power on a power meter. The topic of my video is going to be a little bit different. It's going to be talking about issues like sampling torque, how fast, how many samples you need to take, error, consideration of averages, which is something that's probably underdone on this side of YouTube. And Peak Torque touched upon it, and I'm trying to jump in on the back of that, and maybe talk about how some power meter companies aren't doing what they ought to with power meters. So what's my background? Well, I was an all right club level cyclist, I'd probably call myself. Managed to sneak onto the podium with YouTube celebrity Jesse over here. It's in a development team, but yeah, average cyclist. I'm an engineer, electrical engineer by trade. I work in aerospace, but I'm trained as an electrical engineer. And I think that this is maybe an under talked about topic in power meters, which is the electrical engineering perspective. Because I get the sense that these companies like Shimano, not to point fingers, they're fundamentally mechanical engineering companies. And there's a tendency for electrical engineers get shoved under the bus by mechanical companies that are very focused on the mechanical engineering aspects, because they're told to meet a very tight set of requirements and constraints. And I think that's what's happened with some of these power meters, is that the electrical engineers haven't had much to work with in terms of design flexibility, and that's led to some errors. All right, so what's my history with power meters? These are all the power meters I've owned. This is not just a set of random power meters. I've owned every single one of these plus a bunch more. So the first power meter I had 10 years ago was a Power Tap Hub. So I was one of the first to grab a power meter in Sydney, I reckon, right after I started cycling. And then, yeah, got another Power Tap Hub. These are great units. Stages, not so much. Assume they're better now. Had a couple of Power 2 Maxes, they were fine. Quark, best power meter in my opinion. Favero is also up there, but I haven't used Favero, but Quark, can't speak highly enough of it. I had a Tax Neo as well, and a couple of Wahoo kickers. Plus I've got another smart trainer now, Jet Black sort of smart trainer. So I've got a pretty wide range of experience with power meters. I have found that these left crank power meters just are not accurate, and they never do. They never spit out the numbers that I'm expecting, and they never match with the power meter. That could be my wonky legs, but I think there's some serious issues with the Shimano power meters. Also the right power meter, not just on the Shimano power meter, but also on Pioneer, on 4Eyes. I've always found it to read low. So take with that what you will. We're not going to be talking about my personal experience here. We're going to be talking about numbers. So let's get into this paper that Favero published, because Pete Talk alluded to it. In particular, he alluded to this section up here, which is basically the relationship between power error and the variation in angular velocity. So if you don't know the background of this test, Favero essentially took a whole bunch of cyclists and they used their power meter and computed average using two different methods, computed average power using two different methods. So they basically averaged, for each pedal stroke, they averaged angular velocity and average torque and multiplied the product of those two together. And then they also computed it using instantaneous angular velocity, which is element-wise multiplication of torque and angular velocity. First thing I should note is that they're absolutely correct in their conclusion that you can't just take averages and multiply the averages together and expect to get the average result of the quantity that you're interested in. So for example, power is the instantaneous power is the product of instantaneous torque and instantaneous angular velocity. And if you were to average torque, average angular velocity, and multiply the averages, you're not actually necessarily going to get average power. And whether or not you get it, the extent of the error depends on a number of factors. The first factor is, like, from a statistical perspective, is the correlation between those two variables. So if those two variables are tightly correlated and they're not linear, then you're going to get an error, because the definition of like a joint distribution is including the covariance between two variables. So that's one aspect. Another way of looking at it is in terms of functions. So you can consider torque and angular velocity to be continuous functions of time. And if you take the average value of a function and the average value of another function and multiply them together, you don't necessarily get the average value of the product of the functions. It's just a mathematical reality. So Favero are completely correct in their skepticism of averaging where it's not appropriate. Having said that, under normal circumstances in their own testing, there generally aren't big errors. So for example, on the smart trainer, there's actually, I think that they've performed a bit of a category error here, which is creating a bit of confusion. So the real underlying variable here isn't variation in angular velocity, because that's a bit of an arbitrary measurement that they've taken, which is the highest value minus the lowest value divided by the median value or something like that. So this is, you can see basically in the data set that there's clustering. So there's clustering down here, and this I'm 100% sure corresponds to the tests that are done on circular chain rings, and this cluster here corresponds to the set done on overlays chain rings. So the correlation, this R-squared value, in my mind, and I've done some testing on Python of this data set, it's all coming from this category. So this is basically an example of Simpson's paradox, where they've combined sort of two different categories of data, and the correlation emerges from the categories and not the continuous data itself. So I'd be very skeptical unless you're writing on ovalized chain rings, where there is maybe a bit of correlation here, I would probably be more concerned about this part of the data where there is no real correlation. Okay, so, and also I would say that their methodology, their theoretical analysis, which we're going to get into right now, doesn't actually have anything to say about variation in angular velocity. So let's get down to their theoretical explanation for why there's error when you compute power using average angular velocity. All right, so what are they saying? There's a lot of maths. Sorry for anyone who's not like maybe an engineer or done maths courses. I'll try and go through this as much as I can, but I'm not a maths tutor. So yeah, essentially what they're doing here is they're expressing power as a product of essentially torque, this force function, and this angular velocity function, and they both vary with time. They're both claiming sort of reasonably that force is something which changes across time. It's continuous with time, and angular velocity is also continuous with time. You can sort of prove that with angular velocity in particular, right? Like any sort of velocity is a continuous function of time. Force could change in sort of a stepwise fashion, but this is reasonable, I think. And so they're expressing power as the product of these two quantities, which is correct. So power, force times time times the lever length. And then they're considering average power. So the average power of a pedal stroke is the integral of power across the pedal stroke divided by the period of the pedal stroke, which is the average power, work per second, right? So that's a reasonable, sort of reasonable decomposition they've done here as well. They've now substituted in their expression for power into here. So force is a function of time times angular velocity is a function of time. That's reasonable. And then this is where they've done something interesting in my mind, which is they've expressed force and angular velocity as what are called a Fourier series. So implicit in this is the idea that you can express a pedal stroke, either the angular velocity term or the force term, as basically a signal that is fundamentally periodic. And I don't think that's true. I don't think you can express a pedal stroke as something that's periodic in the pedal stroke, because otherwise you wouldn't be able to accelerate, right? If you weren't applying, if you're applying constantly periodic torque that's completely periodic, you wouldn't be able to ever ramp up your velocity, for example. So, but we'll run with it. I mean, in steady state conditions, this is a reasonable approximation, right? And actually you could get error from other considerations, like the fact that you've got harmonic components, frequency components that are outside of the harmonic range, that are subharmonic, for example. Sorry if that went over a few people's head, but I'm just griping a little bit with their methodology, but it actually doesn't impact the outcome in my view. So what are they saying? Well, they're saying you've got a fundamental pedal stroke, and as Pete Talk said, a pedal stroke has a peanut shape, and if you look at that over like a time in a time domain, so time on the y-axis, time on the x-axis, torque or force on the y-axis, it looks like a sine curve. And because it's complex, because people aren't perfect machines, you have a number of what are called harmonic components that basically distort the shape of this. And it's one of these beautiful results in maths that you can express any periodic signal, no matter what it looks like, as the sum of sine and cos waves. That's what they've done here. So they've said you've got a force function of time, which is expressed as its Fourier series, and an angular velocity function of time, also expressed as its Fourier series. So interestingly here, they've got two phase components, right? They've got phi and theta, phi or psi, theta, right? And so this is the phase component of force, phase component of angular velocity. And what are they doing here? Well, they're basically doing a binomial expansion. So they've got this inner product here. They express it as a Fourier series. They substitute it in, and they get a number of terms on the outside. So what this is here, the first term is your important average by average term. So if you were performing the average of torque, average of angular velocity, you would get that term, and that would be your power value. And then they've got this term, which is basically the average value of force times the harmonics components of angular velocity. And then the opposite of that, the average value of angular velocity times the harmonic components of torque. And then you've got this double sum here, right? And so interestingly, like the second and third term, these two terms, they cancel out because you're integrating a cos or sine wave over an integer multiple of its wavelength, right? So, you know, if you're talking about the third, fourth, fifth harmonic, you're integrating basically 5 of those over one pedal stroke. So the average value of cos and sine over an integer multiple of its wavelength is always going to be 0. So you get a cancellation, which is nice. You get a cancellation of those two terms. So they've basically reduced this to a problem of the double sum. Now, the double sum is interesting because if you have a dominant first harmonic and you've got a phase shift of 90 degrees, so you can see over here, the contribution of these harmonics in any case is 0 when they're shifted by 90 degrees. I just want to say that this is a very Italian article. This is obviously published originally in Italian. I just love the title. It's Influence of Angular Velocity of Pedaling on the Accuracy of the Measurement of Cyclist Power. It almost sounds like a Latin translation of something, but anyway, it's just an interesting way of translating the article title into English. Anyway, so what they're saying here is that in case that there's a harmonics that phase shifted by 90 degrees, there's going to be cancellation. So realistically here, you're going to get error when you've got like a dominant second harmonic of at least of both of these terms, right? Or like when there's a 90 degrees phase shift, or if the phase shift is like much different from 90 degrees. So like, for example, if you had a case hypothetically, I'm sort of foreshadowing here a little bit. If you had a case where you've got a dominant first harmonic of torque and angular velocity, right? Or even a dominant first harmonic of angular velocity and a number of harmonics of torque, then you're really only going to get error when there's a big phase shift. So this is just interesting. So effectively, they've said the same thing here. I'm sorry, I'm rambling on a little bit with this maths, but it's kind of interesting that you really you get error from this double sum term, and it is very, very dependent on this phase shift, this phase relationship between your torque, the harmonic of your torque, and the harmonic of your angular velocity. So why does this not really connect with their conclusion? Their conclusion is really about variation in angular velocity, right? It's really about variation in angular velocity. But as you can see here, there's really not much of a visual correlation between the variation in angular velocity, sort of out to here, and the error, right? It's all pretty much scattered, and there is a little bit of a correlation here. But I think there's a categorical difference in these data sets. This is the non-circular chainring data set, and a non-circular chainring is necessarily going to introduce oscillations in angular velocity. That's the whole point of a circular chainring. And the phase relationship of that is something which is very different to what's going on here. So what we're really interested in here is, well, why do you have oscillations in angular velocity with circular chainrings? Put non-circular to the side for a second. We know that's an issue. Everyone's known that's an issue for a while. Why do you get oscillations in angular velocity when you are using circular chainrings? Well, the simple answer is, if the terrain's constant, you get that because it's induced by oscillations in torque. And there are factors that we are going to discuss now that actually are going to predict the oscillations in torque. So let's get into this this sort of model that I've built. This is a very simplistic model. Hopefully no one has too much of a problem with what I've done here. But essentially I've modeled every angular position, and at every angular position, you've got a torque, which is essentially the average value of torque plus a harmonic term. And this is a harmonic parameter. This is the magnitude of the harmonic term of torque with respect to the average value. So 100% means that you've got an average value of torque and it touches the 0 point here. Any bigger, it'll go to negative. Any smaller, it won't touch the 0 point. And then the second harmonic of torque, these are phase relationships, and this is the harmonic number. So essentially the frequency of the harmonic. So it's like the fifth harmonic in this case. And then I've done the same thing for cadence, and I've spat out what the torque looks like. So this is obviously a really weird pedal stroke. Hopefully no one's pedaling like this. And this is the angular velocity. So I think the first thing to do is just to show statistically that like variation in angular velocity isn't causing an issue in and of itself. So for example, if we set this first harmonic, the second harmonic of torque to 0, just for some realism, right? So this is like a very idealized pedal stroke, and let's introduce some randomness into the angular velocity. So these are just random oscillations, which really could come from anywhere. They could come from the environment, they could come from instrument error. So I'll note that this is a very complicated little Excel formula, but essentially what we're doing here is we've got a normal distribution centered around the average value of angular velocity, which is calculated sort of kinematically here. And then it has a standard deviation, which is like a parameter, which I'm going to put in now. So the standard deviation could be like 5%. That's quite a big oscillation. So you'll note that 28.6%, that's like bigger than almost anything we see in this data set, right? And that's just randomness, right? That's complete randomness. So max minus min IAV is the same formula that they use here. So it is maximum minus minimum rotational speed in the pedal stroke compared to the average speed. So that's exactly the same formula I've used. So that's really substantial error, but there's no power error whatsoever, right? The average power is exactly the same as the proper power, right? I'm calling the proper power the IAV calculated power, all right? So that's an interesting result, that this introduction of error, random error, doesn't have any impact. So this is really, they're hiding what the real correlation is behind this basically fudge variable, which is angular velocity variation. That's not really what we're interested in here. So anyway, let's get back here. So now what happens if we introduce a first harmonic of cadence, right? So we introduce a harmonic of cadence, which is, let's call it like 10%, right? Probably needs to be a bit more than that. Right. So if you introduce even the first harmonic, this actually doesn't have a substantial impact on the error here. I'm just trying to orientate myself because this seems like quite a big value. Maybe it needs to be a bit smaller, 0.3. Right. So this is like quite a substantial variation in cadence throughout the pedal stroke. So if we get rid of our random error, you can see that we've got like a really, really big variation now. This is even way bigger than in the data set that we saw. So let's bring it down even more, down to 0.1%. So this is a reasonable variation in angular velocity. And there is no error, right? So you've got a big variation. It's like you're climbing a hill or something like that, and you still haven't got any error. You've got 20% variation, but you don't have any error. Well, why is that? Well, the first reason why that is because of this phase angle value here. So this phase angle is the phase relationship between torque and angular velocity, and you can see it's 90 degrees. Now, if I bring that down even a little bit, down to 85 degrees, you're starting to see the introduction of error, right? 80 degrees, you're starting to see more and more error, right? So there's almost like a linear relationship. I brought that down from 90 to 80, and you're seeing a 1% error now. Right, so there's a big dependency on the phase relationship of the first harmonic of angular velocity and the first harmonic of torque. What happens if we introduce the second harmonic? It will be smaller. It will have to be smaller for reasons I'm going to go into in a second. So if we make the 0.01 or 0.05 even, you can see there still isn't much error here, right? And if I introduce the second harmonic of torque, which is say 30%, right, you're still not getting much error here, right? And there's even a phase angle relationship. So this is not the harmonic aspect of this is really like a bit of a red herring as well. It's got nothing to do with how messy your pedal stroke is. That's averaged out, right? So that's averaged out. What is the primary determinant of error here is this phase relationship, the phase angle relationship. And it's set to 90 degrees here. Well, why is it set to 90 degrees? Well, that's a mechanical question, right? So let's get into this next sheet. So essentially, you can take the cyclist as a system and model them as a mass damper system, right? And so what you've got is, cyclist, he's applying force as a function of time, just like Favero said, and this is leading to a change in velocity, which is expressed by this sort of kinematic equation, right? So you've got the force that the velocity is a function of the inertia, the resistive force, and the force that's being applied. So this is a mass damper sort of model of a cyclist. So you're applying a force into a damper, which is basically wind resistance. Wind resistance is like a damper, a velocity dependent resistance, and the inertia of the cyclist is resisting that is basically resisting changes in velocity, right? And so you can then express this system in what's called the Laplace domain. So you can talk about it in terms of frequency dependence, right? And the beauty of this is you can see here that there is a frequency relationship, right? So when you're pedaling at a higher RPM, this error that we're talking about here gets smaller, and we can actually validate that in the original data set, right? So we can see here, there's no relationship here between angular velocity variation and power variation. But what you can see is 70%, 90%, you can see visually here that there is less error when you're pedaling at a higher cadence, all else being held equal, right? You can see that. And you can see that here, identical sort of conditions, that when you're pedaling at a lower cadence, right, FTP 90%, 90%, you've got more error. You can see that. And you can prove this from the Laplace domain as well. You can say there's a frequency dependence here, and that when you have a high velocity, when you have a high angular velocity, a high frequency, then you're going to get more damping of this mass. This mass is going to actually attenuate some of the force changes. The force changes from the torque that you're applying that's kind of spiky. It's going to attenuate it because it's at a high frequency, right? So what I've built here is basically a model of this system, and we're going to use this to check against the outcome from Favero. So, and there's going to be some error here because I've basically arbitrarily picked parameters. But you can see here, for example, we're pedaling along at 10 meters a second, 36k an hour at a gradient of 0%, 80 kilocyclists, that's me, 85, 90, something like that, right? And you can see that there is like a dependency on cadence. So if I bring that down, the error increases, right? And increases in a similar way to the error that we see in, someone's just saw my Olivia Rodrigo fucking Spotify called out. Yeah, so you can see the cadence relationship here. You can see it here as well. You can see the error as a function of your cadence. So bring it back up to 90, reasonable cadence. So what we also saw from here is that there is more error when you're riding on a smart trainer. Now, why is that? Why is there more error on a smart trainer than outside, right? Well, that's a function of your mass, right? So the mass is, when you're outside, you're 85 kilos, right? But when you're inside on a smart trainer, the inertia of the flywheel is much less, particularly on this magnetic trainer that they use. It's more like probably 2 kilos, right? So even if we set it to 4 kilos, you can see that introduces a whole bunch of error here, like 8%. That's obviously an overstatement, but there's a substantial introduction of error from the having a much lower flywheel mass. Now, there's mechanical reasons why I don't think this is a good model when you're talking about magnetic smart trainers. But one of the reasons is that the way this formula is calculating it is, and I should run through the way the formula works, right? So you've got this sort of algorithm. So you put as an input your velocity, the gradient, your mass, your system mass, so bring it back up to 80, your cadence, and the power's calculated. So set that to yellow. Power's calculated kinematically. So there's your coefficient of wind resistance, and then there's like your gravitational term here, and it calculates the force, then it calculates the net force, which is gravity removed. So as in up here, then it calculates a resistance, like an electrical resistance. And it computes the angular velocity based on the cadence, pretty straightforward. Then it calculates what's your reactive impedance, which is effectively a term that depends on the frequency, so the angular velocity, and on your mass. And then it calculates a phase angle relationship between the resistance, which is up here, the wind resistance, and the reactive impedance. So then it computes the amount of harmonic work done, so how much work is done by that first harmonic, and then it calculates the error from that. So it's actually pretty straightforward, but the error would likely come from, the magnetic resistance, is that really the same thing as like wind resistance? Maybe it's linear for a certain portion, but you've got issues like magnetic saturation, like it could be non-linear as well, could effectively be similar to gravity, in which case you wouldn't get this effect. So this has got limited use in terms of determining actual numbers. But you can see when you've got like a much lower mass, right? Much lower mass, you have much higher error, right? Because you don't have the same attenuation from your mass. So the force oscillations are producing bigger angular velocity oscillations, right? What's the other effect? So we saw the cadence effect before, going up a hill, right? So, you know, outside, there's no error, 0.04%. Your quark's fine, right? Like every power meter is fine when you're just pedaling around outside. What if you're pedaling up a hill, round ring, on the road, seated? Even at 90 RPM, there's really no error here. How's that different? Cadence 90, cadence 100. There's really no error here, right? So here there's 0.5% error, 0.47, 0.57. You do have higher angular velocity variation, which is true. But that angular velocity variation is induced by the fact that the forces on the system are higher. So I'll sort of establish that now. So let's say that you're pedaling at 5 meters a second on a gradient of 5%, right? Well, your power is 233.7 watts. So it's just calculated sort of kinematically again. So your force, this is the force that the system's applying. So this little cyclist here, you can see the propulsive force. He's applying a force due to the resistance and a force due to gravity, right? So he's applying those forces. So that's the force, but the net force that is actually on the wind, which is how you calculate the resistance, is should be, this should be 7.5 on C30. Right. So yeah, that's the net force on the wind, 7.5 newtons, right? So because you're not talking about this force here, because this has got a gravitational component in it. So you can see here that there actually isn't much error, but then again, they're probably riding around at a lower cadence up a hill. So they're riding at, say, 60 RPM, and they're probably riding at a bit of a higher power as well. So they're probably more like riding at like 7 meters a second. So you're getting close to the numbers that we saw here, right? So this is the real reason why you're getting error. You're getting error essentially because your power is higher when you're climbing up a hill, the forces are higher, you're at a lower cadence, and you don't have this attenuation from mass the same, because you have a higher force. The actual inertia is the same, but you experience higher oscillations in angular velocity just by virtue of the fact that the forces are higher, right? The output forces are higher. The resistive forces, when you stop pedaling, when you've got a dead spot, gravity's really, really arresting your movement, right? So that's why you get these big oscillations when you're out on a hill. But fortunately, for riding up a hill, this changes the resistance goes down. So the resistance goes down, and because the resistance goes down, the phase angle relationship is actually more favorable. So that's why, these errors are not really that substantial. The real errors we're talking about are errors on the smart trainer, and even then, they're not. These are within 1%. So they're within 1%, but it's the circular chain rings are really. That's why this is a whole kind of mountain out of a molehill. It is good that Favero are making reliable power meters and they're thinking about everything, but the reality is that this is not a major concern in most circumstances. We can model out circumstances where it might be a concern. Let's say if we're going at like 5 meters a second, so 18 kilometers an hour up an 8% climb. It's still not a big issue, but 50 RPM, it's still not producing significant error. So I would say that in most circumstances, there's not going to be an error from under steady state conditions. But the more interesting question is, what about under transient conditions? So what if when you're accelerating? This is where we see Shimano underrating and a lot of power meters underrating, and there isn't a difference there. And this is something which I'm going to release in an actual paper because it requires a bit of time domain modeling, which is more complicated than the scope of this video. But you are going to get errors there. You're going to get errors when you're accelerating up a hill, particularly at the low cadence. You're also going to be getting errors, predicted errors here. And it would be interesting if someone tested it on a Shimano power meter, because, and I'll discuss why I'm talking about Shimano power meters in a second. But when, for example, you're pedaling into a headwind, so you've got a 0% gradient and you're riding around at 10 meters a second, but you're riding around at 500 watts, right? You get a bigger error, right? You get a bigger error because you've got more resistance, you've got a higher phase angle relationship, you've got like a lower phase angle. There's a lot of factors. So, or even if you're riding around at like 8 meters a second, 500 watts, right? So if you're running into a headwind, then you should see more error here. This is actually a condition where you could get marginal effects like this 1.86%. And this is something that I've kind of, in the back of my mind, noticed is like if I'm running with my Stages power meter, I get more error when I'm riding into a headwind. It feels really hard. Maybe it's just my pedal stroke, but is this error coming from fundamentally? Well, it's fundamentally coming from a phenomenon called Jensen's inequality, which derives from the fact that the relationship between the power required to produce a certain velocity for a cyclist and the velocity are cubic. It's a cubic relationship. So, to produce a 10% increase in velocity, you need to basically produce 30% more power. And that means that if you're oscillating about a certain velocity, then your average power requirements, even to travel the same exact distance in the same exact time, are going to be higher. Because every second you're above the power and speed that is the average value, you need to produce more power, and it's not going to be made up for when you're traveling below that velocity because of the cubic convex relationship between power and velocity. So essentially, what every good cyclist knows is keep your speed pretty constant. If you're trying to maintain the best average speed and minimize the amount of power you need to produce, keep your speed as constant as possible. And that's true within a pedal stroke as well. But the important thing is that this is true, especially outside. So like when you're traveling outside on a flat stretch of road, this phenomenon comes into play. When you're traveling up a hill, there's a linear relationship between velocity and speed. Having said that, the oscillations are extremely high when you're traveling up a hill because you've got higher forces, and the oscillations are low when you're traveling along a straight, flat stretch of road because you've got a lot of mass and the forces are quite low. So you actually get some like beneficial cancellation of effects. However, the place you don't get the cancellation is on the indoor trainer. And this is why you're seeing a lot of people report errors with like the Shimano power meter on the indoor trainer. I think this is part of the explanation, is because on the indoor trainer, you have like almost the worst of both worlds. You have a potentially quadratic or cubic relationship between velocity and speed. Certainly once you take the control system of the smart trainer into account, you've got something like a quadratic relationship. So, the Wahoo Kicker is emulating a quadratic relationship or a cubic relationship between power and speed at a certain level, right? But also you've got the effect of the flywheel. How is the flywheel actually producing resistance? It's producing resistance via eddy currents. So you have magnets mounted on this trainer and a metallic flywheel, and the relative motion of the metallic flywheel with respect to the magnets induces currents in the flywheel, and those currents oppose the movement of basically the rotation of the flywheel. And that is essentially a linear relationship of force, so a quadratic relationship of power, within certain constraints, right? Which is why you can't make any categorical statements about smart trainers. And what the actual flywheel equivalent flywheel mass is, it's hard to know. So anyway, this is why you could potentially be getting big errors. And also there's a big effect of what gear you're in as well on a smart trainer. And this is why maybe like you're seeing errors in the small chainring and the big chainring on smart trainers. If you're in the small chainring, then the flywheel speed is much lower for the same power, and you're getting, basically, it's like the worst of both worlds. It's like you're climbing up a hill in terms of the forces on the system, but then it's also the sort of quadratic relationship that's producing error here, the convexity that's producing error. So, I just mentioned the Shimano power meter. This is going to be the sort of scapegoat of this video, and it's because they're a big company. They really should be getting this stuff right. But they're the example of a like mechanical engineering company. They make great mechanical engineering products, but just like Apple, they really make a lot of unreasonable demands on their electrical engineers. Apple managed to do it at least, but the electrical engineers at Shimano, maybe they're not sending their best, right? Because like fundamentally, right, they're constrained on this. They're probably constrained aesthetically, right? And in terms of pedal clearance, like you can't mount accelerometers here that would give you an accurate measurement, because the accuracy of accelerometers is like a function of the lever length, because you know the signal to noise ratio will basically increase the further along the crank arm you mount the accelerometer, and you know you also need to create a differential reading between like the sort of gravitational force and the sort of centripetal force. So you know they were constrained obviously here, so they had to use a magnet solution. Magnet solution is very accurate, right? But it doesn't provide any sort of inter-pedal stroke information. And you know what? There's a few things. How the hell are they visualizing anything to do with pedal efficiency when they don't know where the bloody crank arm is throughout the pedal stroke? They're just estimating. The other aspect is left-right imbalance, right? You cannot measure true left-right power if you measure only average angular velocity. That's something which can be mathematically proved, which is like if you don't know the power that each side is producing, then you may as well just be splitting the power stroke in half like a quark, right? And this is something that I'm going to establish in the paper. Don't have time to go into now, but Keith Baker made a point that maybe the alignment of these strain gauges is also causing an error on the new crank design. But I really take issue with this part of the website. This is like the marketing materials of a really big cycling company. And what are they even saying here? They're saying power, watts. Well, power is an instantaneous measurement, right? Is the crank average load per revolution, so newtons, right? Okay, times the crank length, Newton meters per second. In a very trivial sense, the units make a bit of sense, but what this really is this is average power for a pedal stroke, right? And this is average angular velocity times average torque. So they're committing the cardinal sin according to Favero, which is computing averages and multiplying them together. And this is definitely producing error. This is absolutely one source of error when people are comparing indoor trainers specifically to Shimano power meters. So with that, I'll leave it there. I think that this video has been long enough. But yeah, let me know if you want me to discuss anything to do with power meters in a bit more detail in any future videos.